Hi, welcome back. Good to see you again. In this part we're going to investigate differential calculus, and there's going to be quite a few presentations exploring calculus in this course and the applications. So here are the two fathers of differential calculus, I guess you might say. They discovered these ideas around the same time, Newton and Leibniz, and they were both concerned with two problems, and we've got them here: how to find the slope of tangents to curves at any point on the curve, and finding the rate of change in one variable with respect to the other. Hey, what have they got to do with each other? Well, in this presentation I'm going to take a look at Newton's approach and his dilemma with motion problems and displacement time curves. And so we're going to approach it from this point of view, looking at calculus from a point of view of the rate of change of one variable with respect to another. In this presentation, we're going to look at distance and its change with respect to time. So we're back to the velocity thing, because Newton was involved with a lot of that motion problems, as you know, with Newton's laws of motion, and he was a physicist primarily. And then what we're going to do is say, well, hey, what's that got to, that instantaneous rate of change, got to do with slopes of tangents, and bring in that aspect there as well. So differential calculus is certainly about rates of change, so keep that in mind. I want to come down here, and Newton was going along happily when he was using these sorts of displacement time graphs. Not a problem here, because it's a straight line. And you might have seen this before in an earlier presentation. The screen clippings here are from Hayes, Hose and Harris, Math Studies book, second edition. And so it is worth noting, though, this presentation is being done in a slightly different way from that produced in the textbook. I'm using screen clippings and exercises from there, but the way in which I'm introducing it is quite a bit different. So hang on in there and see what you think, and then have a look at the textbook later on. Now, if the plot of distance against time is a straight line, can you see what they've got here? Delta S on delta T. Remember, delta implies difference in. So we're looking at the difference in the S's, that's displacement, with the difference in the time. So that's the slope of that line. And that is going to give us, delta S on delta T is going to give us a velocity. And what have we got here? 160 on 2, it's going to be 80 kilometres per hour. Okay. And does it matter where you do this on the line? I don't think so. Because it's a straight line and it has implies a constant slope. And the slope is the velocity. Here it is, y step on x step. So it implies a constant v. No hassles in calculating v. Newton's really happy at this stage. Well, his happiness was short-lived, because he did an experiment and he got this. Oh, what's happening now? There's time, there's displacement, but the graph of displacement against time is a curve. So, what is the velocity at t equals 4? What is it? Hey, I don't know. Oh, I can work it out. I'll go up here, I'll join 2 points there, and I'll work out delta S on delta T again, and I'll get the velocity. Everyone knows that. Change in displacement with time is velocity. Done it, haven't I? Uh-oh. I don't think so. I think I have a problem. Do you see my problem? Look at this. That's not working too well. There's a gap there. Hey, this is the average velocity between the points I've used, between the 2 points. Did the body actually exhibit this change in displacement with time? No, it's the blue line. and the blue line is under that chord. The chord is an average between these 2 points. This is an important concept in differential calculus, the average. So, Newton was really concerned. What is the velocity right there? Because it's slowly sped up. Slowly sped up here. It didn't go like that red line, that chord went. So what is the v inst? Let's just go back up there. So what is the instantaneous velocity? The v inst right at that point. We haven't got another point to do a delta s over delta t with. This was Newton's dilemma. And this led to his discovery of differential calculus. So, what did he do? Well, let's come down here. I've got a little diagram for you. Come down here and just rub that out now. He said, well, I don't really want delta s over delta t for the chord AB1. That's an average velocity. As you can see, the blue line is below that chord. So the chord, oh well, I really should put here the slope, isn't it? The slope of that chord is the average velocity. I can't use that. I can't use the slope of that. That delta S on delta. B2 would be better. Oh, it's closer. No, B3? B4? Oh, there's not much of a gap in there. The slope of the chord, a chord is, remember, a line joining any 2 points on a curve. The slope of the chord AB4, it's still an average velocity, but it's a better estimate, isn't it? Because it's closer to the behaviour of the body there. See, there's not much of a gap between that straight line behaviour and the actual displacement time curve. He said, though, what is the limiting position? Limiting position as you get closer. Limiting position of the AB varieties, of the AB chords. What's the limiting position? He said, well, the absolute limit of this is the tangent. That's the limiting position. So that equals tangency. And so Newton proposed that V inst, the instantaneous rate of change of displacement with time, was equal to the slope of the tangent. If only mathematically we could work that out. Slope of the tangent at the instant in time that you're interested in. So that was his fundamental reasoning. Now what we've got to do is say, can we measure the slope of the tangent? Well, I mean, if you want to be a bit rough, you could do it with a scale drawing. Hey, that's not maths. How is the maths going to do it for us to find the slope of that tangent? Because that is clearly the limiting position of that average velocity. That will be our instantaneous velocity. Okay, he did some maths now. Hang on, we're going to do some maths. Let's have a look. So here's his maths. He said, well, let's take a displacement time graph. So we're going to go into y and x land. He would have been in s and t. And we're going to use this fairly simple function to track this. So notice this work needs a formula for the displacement time graph. He's going to say now, when x is 1, sub 1 into x squared, and y is 1. So there's the point I'm interested in. I want to know the slope of the tangent and therefore the instantaneous velocity, if we're talking about displacement and time, or the instantaneous rate of change of whatever's up the y-axis, rate of change of y with x. Okay, that's what we're trying to do there. So he said, well, okay, let's draw in a chord. He doesn't like chords much, you know, because they're only averaging the rate of change between the points. So he said, well, let's go out a little bit from 1 to 1 plus h and draw a chord there. So m has the x value of 1 plus h. So he's gone out about h there. What is the y value at that point? Well, to get the y value, you stick it in place of x in the function, so it's 1 plus h squared. So, do you agree that the y coordinate of m is 1 plus h squared by subbing into y equals x squared? So m therefore is the point 1 plus h, comma, missing there, 1 plus h squared. So let's work out the slope of the chord and see if we can find its limiting position. So the closed slope of the chord is y step on x step. Let's take the y's away. Second y minus the first, that's it. Over second x, 1 plus h, take 1. Yep, y step on x step in symbol land. He wanted to do this in general so that he could look at a mathematical application to any function. So when you expand 1 plus h squared, we get this. Take 1. And the bottom, of course, is just the difference between 1 plus h and 1, which is h. So the slope is this thing here, when you simplify that. Now, he said, what is the limiting value of that? He wanted to know, as h went to naught, as m approached your point f along this curve to get to tangent C, what happens? What happens to m? That's what he wanted to know. Well, what would you do? I'd stick h as naught in there, mate, everywhere. Uh-oh, can't do that because dividing by 0 is undefined. So he said, well, I'm going to do something. I'm going to simplify this function by cancelling. Just remember, and I prefer you put it here, with a proviso that h is not equal to naught. So he got an equivalent function, 2 plus h. And then he said, well, what does this tend to? 2 plus h, as h tends to naught, approaches 2. So he concluded the slope of the tangent has a slope 2. Okay, because that was what the chord tended to. Now, a lot of people don't like all these h's not equal to naught here, because then you end up subbing h in. Let me see if I can explain this to you. We have a function here which is undefined when h is naught. When we simplify it, we get this function here which is defined when h is equal to naught. What is the difference between the two functions? Well, there's nothing except at that one point. If we were graphing the function, one would be 2 plus h, if we were graphing that against h, would be a straight line, and it would be defined at h is equal to naught. This one, however, would not be, because it's got an h underneath. It cancels to the same function and has the same limit, but is actually undefined at the point h is naught. This is limit theory, and there isn't a lot of limit theory in this course, but I want to take an example here and just go off on a tangent, small joke, into limit stuff for a little bit here so you get a better mathematical understanding. So come down here with me. And I've drawn a graph of this function here. X squared take 1, divide by x take 1. So let's have a look. Y equals x squared take 1, divide by x take 1. Let's see if we can simplify it. Can you see this is undefined at x is 1, because you're dividing by 1. Okay, let's simplify the top line. X plus 1 by x take 1, difference of 2 squares. Divide by x take 1. That will simplify to x plus 1. Alright, so what happens? Hey, this function here is exactly the same as this one. Oh, I've graphed it over here. That looks like x plus 1. Yeah, that checks those intercepts. This is the graph of y equals x plus 1. No, it's not. With a hole. It's got a hole in it, mate. See this? And that's the notion of limits. I reckon if you can understand this, you've got the limits. Because this function that we started with was not defined at x is 1. It is, however, equivalent to cancelling, provided that x is not equal to 1, to this one, which we can graph. And this one is defined at x equals 1. It comes to 2. So we write this. Watch this carefully now. The limit as x tends to 1 of x squared take 1 on x take 1 equals the same limit as x tends to 1 of its mate x plus 1. Please note that the graph of this and the graph of this are not quite the same. One is equivalent to x plus 1, but with a hole, what's called a point discontinuity, because of this denominator. But limit theory still holds here. We can say, well, as we approach this point, here we go, along the line, starting from x out further than 1, either way, above or below, as we come into x as 1, it tends to the value 2, here it is, tends to the value 2. We can make this function as close as we like to 2 by making x closer and closer to 1. It's just it's different from its mate. This one can actually reach 2, and this one is actually undefined at 2. Interesting theory, isn't it? Now, a little bit of this is required in the course. Now, Hayes and Harris go into some limit properties there, which are technically not examined in the course. But the notion of basic limit theory is. So let's come down here, and I've got the result there that you are required to know. The limit as x tends to 1 of a function, and I've chosen the one we've just looked at, is 2. What does that mean? Since we can make x squared take 1 over x take 1 as close as we like to 2 by making x sufficiently close to 1, it doesn't actually have to be defined at that point. Okay? So this is a very informal definition of limits. We can make it as close as we like to that value by making x sufficiently close to 1. So that's the notion. Please notice that's a big hole there. We can get right up to close to 1. It can be 0.99999 or 1.0001, and we get closer and closer to 2. Okay, so that's the limiting value. Alright, so that's giving you a bit of background to how Newton looked at the slope of the tangent by taking the limiting value of the slope of the chord as you brought 1 point closer. Interesting theory, isn't it? Okay, let's come down here and let's look at the formal approach to this that we have to do mathematically. This is called a first principles, and you only go through all this if this is asked. It's a first principles derivation or approach to finding the derivative function. Let's have a look at what the derivative function is. It's a function that we're going to derive from this slope approach. So here's our basic diagram over here. We're going to start at a point, and it's got coordinates x, f of x. And we could get that f of x by subbing x into the particular function. This point here, we're going to go out to x plus h. So its y value would be f of x plus h. So our general slope for that chord, which represents the average rate of change, doesn't it? Remember, average rate of change, because the curve didn't actually go that way. That was across the top of the curve. The slope of the chord is y of the second point minus y of the first, x of the second point minus x of the first, as before. So this is only a y step on x step expression, generalised for a function y equals f of x. Now we're going to move b closer to a, just as Newton did before, and therefore we want to know what is the limiting value of this as h approaches 0. And we define the slope function as a limit as h tends to 0, and here's your basic definition of that slope of the chord over h. So here it is down here, and there's our fundamental definition. The slope function, that is, we're going to create a function which when we sub into will give us the slope of the tangent or the instantaneous rate of change, instant velocity at that point. And the symbol we use is a dash, to say, well, it's got something to do with being derived from the original function through looking at the slope of the chord. The derivation is that the derived function, which will give the slope of the tangent at an x value, is the limit as the chord approaches tangency along the curve. So that's our derived function. It's called the derivative, and it's got the symbol f dash x, meaning it's been derived from f of x. So it's called the derivative, not the derived function usually, just what is the derivative. And when you say what is the derivative, then you know you're looking for a function which you sub into to get the slope of the tangent. Let's do an example. Okay, so Hayes and Harris here. I've done this in a different order, so we're starting with 3C, not with A and B. Presentation is going to do it differently. So from first principle, find the slope function of f of x equals x squared. You always start off with this, and remember it's first principles. So you start off always, this is mandatory, to start with this slope expression here. You must always put in the limit as you simplify it. Okay, let's have a look. If we had a point on x squared and the x value was x plus h, what would the y value be? Stick it in the x function and it would be x plus h squared. So that's f of x plus h. What's f of x? X squared. And this is always h in the bottom. The x step is always h. We went h further out. We expand it, first one squared, twice the product, plus second one squared, take x squared. Here we are. There it is. There's the crucial step, because we cannot work out a limit of this function while it's got h in the bottom line. It's undefined at h equals 0. So what must we do? We're going to find an equivalent function which is defined at h is 0. So you know your aim here, your primary aim, is to do this. You must cancel h so you get a function that is not got h in the denominator and therefore is defined. And then you sub in limit as h tends to 0 of that. Here, I'd like another step in there. Limit as h tends to 0 of 2x plus h. That's left. And if you sub h is 0 in there, the limit is 2x. And I would prefer not as, but provided h is not equal to 0. What does that mean? What does that mean? Well, if we had x squared up here, it means if we went to the value x is 2, and this is f of x equals x squared. If we went to x is 2, to get the slope of the tangent there, we use f dashed x equals 2x. When x is 2, that equals 4. So the slope of this tangent at x is 2, tangent has a slope equal to 4, because our derived function is that function, so it's got an x in it, which will enable us to find the slope of the tangent at any particular x value by subbing in there. Right, here are yours. Find the slope function for this set here. Just remember you'll have to do your cubes and the power 4 expansions, binomial, in these. So write out the definition, try to follow it through. So I'd like you to try and do those. And once you've had a go at one, toggle forward and look at the fully worked solutions there. So that's question 1 and question 2 there. I've screen clipped at a bit of an angle there, but you'll be able to toggle forward and back as you go to look at the answers to those. Alright, so that's your first job, to stop there and have a go. Later on, you might join me. I'm going on now. And what we're going to do is have a look at a slightly different example. Find the derivative, the slope of the tangent giving function, when I've got a fraction. Can you see the difficulty here? F of x plus h is 1 over x plus h. Take 1 over x. lot harder. Now, Hayes and Harris suggest multiplying by the common denominator, which is that times that, top and bottom. And that's good. Because in the top line, the x plus h will cancel and give you x, and in the other side give you x plus h. So it's a form of cross-multiplying. I don't know whether cross-multiplying is the easy way of thinking about it, rather. I don't know whether you'd rather think of it this way, common denominator, and then this has been times by x, so you have to multiply the top line by x. This is to multiply by x plus h, multiply the top line by x plus h. I don't know whether you want to think of that, and then this, of course, is being all divided by h, so it goes down there with it, divided by h multiplied by 1 on h. So this common denominator idea is the hassle with fractions, and this has been asked in an exam. So to get this final step, I know a lot of people will try and remember it by that goes there and that goes there. Well, as long as you know the maths, I don't suppose using the quickie step of cross multiplication is a problem. So here we have this line, expanding the bracket, taking out x, taking h. We've got this one. You know at this stage, to find the limit of this function, you have to convert it, there it is, to a function which is defined at h is naught. And so we've got here I prefer you put this stage in, neg 1 on x squared plus hx. If h tends to naught, sub it in, it's neg 1 on x squared. So, put in, provided that h is not equal to naught. Okay, I want you to try those with fractions. Gets a little bit stickier with fractions because of that common denominator and simplifying over one denominator, that step there. You might have to study that. Okay, might pause the presentation and have a go. The answers to that lot is right down the bottom here. So there's question 3, A, B, C and D, bit on an angle there. So you can pause that when you're ready. We'll go back and look at the second example, which is another variant. This time got a square root in it. So can you see our problem here? How do you divide h into that to get a function which is equivalent to it, but defined? So you've got to divide h into it. There's no common factor of h in this line. So this is the trick. You need to remember this, the use of the conjugate. The use of the conjugate in square roots. So if I multiply root x plus 1 take root x by root x plus root x, I get the first one squared minus the second one squared. Do you remember? A plus b by a take b is a squared take b squared. And that nicely gets rid of square roots. No square root in that line there. But you've got to do it to top and bottom. And the bottom becomes a mess. Never expand this. You don't need to expand it. You never expand the denominator in first principles. Why? Because this is the dude you want to cancel. Leave it out the front. And now, x take x is no x. So you're left with an h in the top, h in the bottom, and you know it's got to cancel. You're trying to find an equivalent function which is defined at h is naught, so you can find this limit. So it's the limit as h tends to naught, and I'll put another step in here, 1 over root x plus h plus root x, limit as h tends to naught, and when you stick h is naught there, you get 1 over root x plus root x, or 1 over 2 root x. So these are quite mushy. These reciprocal ones or quotient ones, 1 overs, and square roots. They need their own tricks. So here you are. Here are ones with square roots. Here's one with both. Quotient function and a square root. So you might have to work hard on that one. And then finally, you might try to answer this question. Do you see a pattern when you have powers of x? Does the derivative f dash x follow a pattern? So you might like to try that. Okay, I'm going to go down and display these answers now. I paused that earlier, so we'll just focus on 4 and 5 now. So you have to toggle forward and back to those particular spots. This is fairly hard going with these square roots. You're always using the conjugate, if you remember, so that's very, very important. Okay, so I'll leave you with that now. This presentation you might have to split into several parts. There's a lot of work in it, and you do need to use that work, do that work. All right, I'm going to go on now, and I'm going to give you a modified version of that x plus h. Can you see what we're doing here? We have replaced the x by a. Now, this is a shorthand. This is to be used when you want to find the slope, when the slope is needed just at a point, just at one x value, just at one x value. Because what we're going to say, instead of tending to the, let's say, the general point, x here, x f of x, we're going to do like that first Newton example, call this maybe 2 f of 2. We won't come up with a derived function, we won't come up with a derivative, f dash x, we'll only come up with a number. Let's have a look at it. Use first principles formula to find the slope of the tangent only at x is 5. They don't ask for the general form of the derivative. So let's have a look at it now. I'll just come down here a bit. So, we start off with the 5 in there, not an x. It's not the general derived function or derivative. That's f of 5 plus h, take f of 5. So sticking it in the function was x squared plus 2x, I think, wasn't it? Let's go back up and just check that. Yeah, x squared plus 2x. So that's x squared plus 2x. And then that's minus f of 5. So you're subbing in just the known x value of 1 point. Expanding it, don't forget first one squared, twice the product, second one squared, expanding the brackets carefully, and then everything has to go out except the h terms. Because you know, here's a crucial step, finding a function which is equivalent to this, except that one value h is naught. So the limit of our undefined function equals the limit of one that is. And then we can sub in. So what does this mean? We have found the unique value of the slope of the tangent at one x value, not a general derivative. Okay, and here of course, the instantaneous rate of change. Oh, that's a dichotomy, isn't it? Means the same thing, because the instantaneous rate of change Newton defined as the slope of the tangent, or the limiting value of the slope of the average change of that chord. Okay, so down here we'll put in neg 3, and this time the function, if you remember, just back up here, was 4 on x. So here it's 4 over x plus h. Take 4 over 3, which is going to be plus 4/3. Can you see all the algebra is easier if you only want a point? So if you only want the slope of the tangent or the instantaneous rate of change at a point, it's easier to use this x value replaced by a or by the value you're interested in. Simplifying, again h must cancel, and then when you stick in naught, you get, I would like to go here, 4 over 3 by h take 3, the limit of that. I think I'd rather have an extra step in there. As h tends to naught, that tends to 4 over 3 times neg 3, which is neg 9. So the slope of the tangent at x equals neg 3 is that, or the instantaneous rate of change. They are synonymous, they mean the same thing. As Newton came to that realisation when he was looking at the instantaneous velocity and wanted to find the limit of the average velocity, or the slope of the chord between 2 points. Okay, so 3b is quite long, so you might have a look at those. Pause it, and there's a bit more down here. And I haven't put the fully worked solutions. They're the answers down there. All right, so I've only got a couple more things for you. The first one is the calculator. If you aren't asked for first principles, the calculator can give you f dashed of 3 or any value by using two different modes. First of all, here it is here. You can use run mode, and in this one I'm in the math form of run mode. And what do you do? First step, you hit the key options, and up comes this window. You then want calc, so you hit F4, and then you see, here it is here. You haven't seen this yet, d by dx. Now, this is standing for the derivative with respect of x. Now, where that comes from, the d is representing the limit as delta x tends to naught of delta y on delta x. It's that delta notation again. So this is d for delta, or change in, or difference in. So this is still difference in y over difference in x. Same stuff, it's pretty simple. It's the slope of the chord as the bottom part tends to naught. So d by dx is, and we usually put in the function, derivative of x squared with respect to x, or you could put, if you want it in general, dy by dx. It's just again referring back to that. So the calculator uses that, so to choose that, you go to F2, and then if we come down here, and we've got to come down here, here it is. You're allowed to put it in that form. So in this hole, you put the function, there it is, and in this hole you put the value at which you want the slope of the tangent or the instantaneous rate of change, and it comes up with the answer 4. So you may use this technology if they don't ask you to show that or do first principles. There's another way with technology, and that's, same way I suppose. If you're in math mode, that's what the window looks like. You can change that to linear mode and hit options and d by dx, and then you get a syntax problem. You have to then put in the function. This is in linear mode, run mode, in linear form. You've got to put x squared in there, comma, and 2, and then when you hit execute you'll get 4. So this is the form that you must use if you're in run mode, but in linear format in run mode. Okay, slightly different. Still hit options, still choose d by dx, but the syntax here has to be entered slightly differently. Well, the syntax is different. Okay, let's come down here. We can do it in graph mode. So let's draw the graph. Then you go to Shift menu to set up. Make sure the derivative is on. Okay. Then draw the graph. So hit execute, draw the graph, and then coming down here, then you actually have to hit Shift F1 to get trace, and this is what window that you get. It will pop on some value and it will display the value of the derivative or the slope of the tangent or the instantaneous rate of change at that point. If you want a particular point, just hit 6 for example, and this comes up. Hit 6 on the keyboard, and then once you've done that, execute, and there you can actually display the derivative value at any particular x value. It doesn't have to be 6, it could be 6.2. Just enter it on the keyboard, hit execute, and it will trace along to that point and display the slope of the tangent at that point or the instantaneous rate of change. So there's a little introduction for you. There are two notations. F-x, meaning the derived function connected to f, and dy by dx, which is reflective of the idea that you're doing the limit as delta x tends to naught of the slope, delta y on delta x, Greek capital D. So we put it that way. Notice it's not dy divided by x, it said dy by dx, because it's encompassing all of that, the limit thing as well. All right, well, what I want to do now is just to give you what I call an important trichotomy. So out of Newton and Leibniz work, what are we going to get? We're going to get the derivative. Later on we'll find rules. We don't want to go through all this long first principles. So we're going to get the derivative from first principles like we've just done then, or later we might use some sort of patterning or rule. But what does it mean? Here's a trichotomy. It means you're looking at the slope of the tangent at a point, because Newton said he was really interested in the instantaneous velocity, but that was a limiting value of the slope of the chord, which was the average velocity. So what do you reckon? They are all interchangeable. Here he is, instantaneous rate of change. Rate of change. These are interchangeable. When you see one, you should think of both of the others, right? Because of that early work of Leibniz and Newton, where you have a function which has a changing rate of change. This one is increasing at an increasing rate. You can't define an instantaneous rate of change at that point using 2 points. Instead, you're going to take an average rate of change, which is the slope of the chord. Slope equals the average rate of change. And by that theory of Newton bringing this along, the limiting position is tangency, and therefore the slope of the tangent is the limit of that, and it equals the instantaneous rate of change, not the average. It becomes, if you like, compacted down to an instantaneous rate of change by that process. So please remember Hutty's trichotomy here. There are three things. I say derivative, no matter how you get it, you think instantaneous rate of change, and at the same time you think slope of the tangent. If you say slope of the tangent, I'd say, hey, you've got to get the derivative made, and that'll give us the instantaneous rate of change. And around we go. Calculus is fun, and it's quite easily understood if you go through it slowly and look at perhaps that Newtonian approach with motion. Clicks with most people because they understand distance over time is speed or velocity in this course. You might have to pay a bit more attention to direction if you're going to loosely use velocity and speed in physics, and we'll have to look at that ourselves later on. Well, I hope you've enjoyed this. It's a fairly long one, and you really have to take this in pieces, this presentation. But I wish you every success and fun with the problems there. And from me, it's cheers for now. But I've got some more interesting differential calculus later on. Catch you then.